remember that there are two categories of names. Right? There are the names where the cation has a known charge, where it's always the same charge. You're pretty much talking about the first two groups, and then also aluminum and zinc. But basically the first two is what we'll focus on. And then you have the other ones where we don't have a fixed charge, all the transition metals in the middle that can take various different charges, and then some of the ones that kind of creep over onto the right underneath the staircase also. So in those cases, like with lead here, we look to the anion, the negative ion, we figure out its charge, and then we go back and figure out the metal's charge from that. So if we have something like, let's do a nice review here. How would we name K3P?
Do the parentheses? Do you want us like to name them?
Well, we have to decide if we need the parentheses or not. So look up K, which if you don't have a periodic table is potassium. And P is phosphorus. So how do we change the name of phosphorus to make it an anion? Phosphide, right. So we can start and go potassium phosphide. Now, do we need to specify the charge of potassium with parentheses? You're saying no, why not?
I'm not sure.
You're not sure? Well, it's good that you have the feeling that you don't put the parentheses, because that's correct. Does anybody know why?
It's on the left, and it's not a transition.
Right, it's not a transition element. We always know what the charge on potassium has to be. It always has to be +1. It never takes another charge. So if we know it's going to be +1, it's always +1. We don't need to specify that it's 1 in parentheses. Right? So let's look at a different one where we might need to. AU is, you know, gold. So we've got gold, and what's the other part of the name going to be? Oxide. So do we need to put the parentheses here?
Yeah.
Yeah, why?
Because it's,
Because in the middle?
yeah.
Yeah. What do we put in the parentheses?
It's either 1, 2, 3. No, it's 5.
Well, let's see. What goes in the parentheses? What quantity goes in the parentheses? The what?
So we
You're
have to
right.
even out.
Yeah, the charge of the element. So the charge on the element, or the oxidation state, we might say, is another way of saying that. But the charge. How do we find that? How do we find it for something like gold? Right. We have to see how many we need to cancel out the oxygens, because we know the charge of oxygen. What is oxygen's charge always as an ion? -2. And we've got 3 of them, right? I like to just write them all down. What's that total negative charge? 6. So then how much total positive do we need? 6. Okay. We've only got 2 gold atoms based on the formula. So what do they what do their charges have to be? Yeah, they each have to be +3, so they can be 6 together. So that means that we put a 3 in here to show that each gold ion has a +3 charge. Good so far? Maybe?
You said
Starting to
oxygen
remember
always
this?
has a -2 charge, -2 charge.
Yeah, right.
So I forgot how we would do like the first one.
Mm-hmm. This one? What do you mean how we would do it? How would we get the name?
Potassium would be a +1.
Yep.
Okay.
So we've got 3 potassium 1s, and then phosphorus would be 3-. Phosphide is also always 3- because we can find that from the valence electrons. We know that phosphorus has 5 valence electrons, meaning it needs 3 more to satisfy that octet rule to get the full shell. So if it gets 3 more, it's 3-. All right, you ready to get trickier? Not trickier, just some more stuff in there. And we'll keep practicing this too. Okay, the next part of this that we've actually encountered before in lab is what we call the polyatomic ions. Polyatomic just means more than one atom. So if you notice, when we go back here, all of these examples, there's just been one type of atom for each ion, like a lithium ion or an oxide or a phosphide or a bromide, whatever. There's actually lots of ions that have multiple nonmetals in them, and we have to think about them a little bit differently. So for instance, one of the compounds that we used in lab last week with the flame tests was this.
Was this an unknown or was it?
No, this was one of the known ones. This was strontium nitrate. So that's the formula, and the words were strontium nitrate. So this now looks a little bit different. We've still got strontium, which is in the second row or second column, second group 2A, SR. So it's a metal, and we know it always has a 2+ charge. But now we have this other thing, nitrate, and it's made up of both nitrogen and oxygen. And it's really an atom of nitrogen with atoms of oxygen around it, bound together. And that is one whole unit. So the nitrate ion is a whole unit of NO3 with a 1- charge. And that means if we want to balance out a +2 charge, we have to get 2 of those whole things, and that's why we have these extra parentheses with the 2. So we need 2 of those whole things to balance out the strontium. So how do you figure out that NO3 is -2? Go ahead, what were you going to say?
Nothing. Because I was way off.
Okay. I mean, you don't find NO3 on the periodic table. It's actually made up of nitrogen and oxygen. And the answer is that actually we just kind of have to remember that that's the formula. There are ways to figure it out, but to get into that is beyond what we're going to do in this class anyway. So we've got a short list of polyatomic ions that you simply need to know. And we're going to go through them right now. So we've got nitrate. We have hydroxide, which is OH with a -1, like sodium hydroxide. We have carbonate, like in your carbonated beverages, which is CO3, and that's a 2- ion. We have bicarbonate, which is a lot like carbonate but with a hydrogen on it, and it's just a 1-. Was that it? No, a couple more. Phosphate, which is PO4, and that's a 3-. Sulfate, SO4, that's a 2 minus. And then there's one positively charged that we're going to look at, and that is ammonium, which we've also used in lab, which is NH4 plus. So there are a bunch of these. There are lots and lots, and the book has a huge table of them, and you'll need to use that table when you do your homework. But for the exam and for the quiz next week, I'm just going to ask you to learn these 7. Right? And those are the ones that are posted on Blackboard under the course objectives, if you forget or you don't have them in your notes or whatever. These 7, you have to know the formula, the charge, and the name. All right? It's not enough to just know the formula and not the charge, because you won't be able to write the formulas appropriately. The good news is the rest of it works the same. All the other stuff about naming with the parentheses or not is all the same, but we use these ions instead of the other ones. Let's do some and try it. So let's say I want to get the formula for calcium hydroxide. I need to put my ions together and then figure out how to balance out the charges. What's calcium? Ca plus 2. And what's hydroxide? OH minus 1. So can I just put them together and I'm done?
No.
Why not?
Because the calcium has a positive charge of 2.
Right.
And the hydroxide is negative.
Of 1, right? So they're not going to balance each other out. How do I fix it?
Balance out the hydroxide.
Yeah, we need another hydroxide. We need 2 hydroxides for every 1 calcium ion, because we need 2 plus and 2 minus. Okay? And the way we write that together is we write the calcium, and then we have 2 whole hydroxide ions. Notice also we don't write the name in the charge.
Wait, so you don't write the name?
Or the charge in the formula. Sorry, I misspoke. We don't write the charge, like we don't put the little minus and the plus in the formula.
Okay.
We assume that they balance out. So that's going to be our formula for calcium hydroxide. Why is it in the parentheses? Well, because if we wrote it like this, that would be something different, because this would tell us that we had a calcium, an oxygen, and 2 hydrogens. And that's not what we have. We have 2 whole hydroxide units. So we need the parentheses around them. Yeah. Calcium is in the second group, and so it has 2 valence electrons. It wants to lose those 2. All those are going to have a 2 plus charge. All right, let's try to go the other way. I'll give you we'll get rid of our names and see how well we remember them.
It was CA2.
Let's try another one of these. Potassium phosphate.
The group number tells you what the charge is.
For the first 2.
And what else?
Then we have to do other things. Like with the anions, we add electrons to them to try to get to 8. And however many electrons you add, that's the negative charge. Mm-hmm. Yeah. You can go back and review the stuff from last Wednesday when we kind of went through that, or I'm talking about it. But yeah, we can pretty reliably talk about 5A, 6A, and 7A as being -3, -2, and -1 usually. And then all the other ones, we have to look at the other things to figure out what it is.
That was +3.
We don't have nice rules about them. So what's potassium?
Plus
Okay.
K. And what's the charge?
one.
+1. And what about phosphate? Yeah, PO4 minus 3. So how do we put these together?
We add 3 more. Phosphate.
Well, 2 more to get 3 total, right?
1 more.
We need 3 of these to get 3 plus to balance out our 3 minus. Yep, go ahead. Yeah, the only difference is in this case, we don't need the parentheses because there's only one of them.
So we only need 2 more potassium to balance out phosphate.
Right, because we now have 3 total potassium, 3 plus potassium, 3 minus phosphate. Let's try this one. So this time I'll give you a formula and you can give me the name. CuSO4. What's Cu? Copper. Anybody feel confident about this yet?
What's the charge on copper?
Well, what is the charge on copper? We don't know, right? Copper's in the middle. Copper's a transition metal. So we don't know the charge on copper. So how do we figure it out?
Well, it's SO4 minus 2.
Mm-hmm.
So you need 2 copper.
Right, so copper must be 2. So we know, yeah, let's check. So we know sulfate is minus 2, because we just have to know it or we look it up in the list. All right. We know we only have 1 atom of copper, because there's no little number down here. So this copper must be also plus 2 to offset the 2 minus. All right. That means that when we write the name, yeah, we can put a 2 in parentheses. So this is copper 2 sulfate. The other common form of copper is copper 1. So let's see if we can write a formula for copper 1 sulfate. Everybody get it? No.
Would be
So you
CU
to
Right. Well, except for the 2.
How'd you get it?
How'd you get that?
Well, since it's a one Cooper, that means that we have to have like two of them.
Mm-hmm.
So each of them will get 1 charge.
Right. So we look at this formula and we say, okay, copper 1 means that it's copper plus 1. And it's important to remember the number in the parentheses is the charge, not the number of atoms. It's the charge on each atom. So we've got copper plus 1, and we've got sulfate, which we know is still SO4 2 minus. In order to get those two to balance, we got to have another one of these. And that's where the 2 comes from, so it's copper 2 SO4, Cu2 SO4, and that's called copper 1 sulfate, because it's copper plus 1. All right. Keep going. Let's try another one. So you can come up with a name for that one. Everybody feeling good about this one?
You want the name of it?
The name, yeah.
Cobalt 9.
So what's the name of the NO3 thing?
Nitrate.
Nitrate. So this is going to be. And you said there's something in parentheses? 9? How'd you get 9?
3 cobalts down. I mean 9 cobalts down. 3.
Well, let's think about it. So we've got each nitrate is NO3 minus 1. All right, each of those is minus 1. So does that change what you put in the parentheses? What do you put in there then? 3. Because we need a 3 plus on the cobalt to balance out the 3 minus on the nitrate. All right. We'll keep practicing these. There is plenty of practice with these through the book, online homework, and all over the internet if you look up practice naming ionic compounds.
Or like chemistryfordummies.com.
Okay,
Seriously.
I don't know that one.
I was just on it this afternoon.
Okay.
Does it help?
Would have been helpful for like, the first test.
Well, now you know for the next one.
Yeah.
Yeah. All right. So the last part of our naming is going to be dealing with molecular compounds. We're going to talk a little bit about what that means, what those are. Now that you're so good at naming everything else. What? I know, but you know. So actually, we should talk about this a little bit. One of the issues I think that comes up, you know, with being prepared for the test and everything, the way this class is set up, this is a very difficult format. To have a week's worth of information in a 3-hour session on Wednesday night is tough because there's no way you can pay attention the whole time. Even if you're really trying hard, it's just not going to get in your brain. Which means that a lot of the stuff we do every Wednesday, really you have to go then redo on your own to really study and get it. So it's easy to go home after your Wednesday night class and kind of forget about chemistry for a while, maybe do your lab reports, but not really do homework or think about it. You got to really schedule some time in to work on chemistry every day, even if it's not that much, but every day, just to kind of keep it in your brain, because it's tough when this is the only time over the whole week that we really get to be together to talk about this stuff. So, that said, let's go talk about some more stuff. Let's talk about molecules. Molecules occur when atoms get together and share electrons. Remember, ionic compounds were when atoms had different charges and simply kind of stayed close to each other because positive and negative attract. In molecules, they're sharing electrons. So if we go back to those electron dot diagrams we did, where we would take something like hydrogen, and we would say hydrogen has how many valence electrons? One. One valence electron for hydrogen. When we draw a little dot next to the hydrogen, we're saying that's its valence electron. Well, hydrogen is not terribly stable like that, so it either wants to lose that electron and become an ion, or it wants to get one more so it can have a full valence shell too. The way it can get that one more is by sharing with another atom of hydrogen. So we can take another hydrogen with its one valence electron. We can kind of put those electrons together. And so this is going to be a hydrogen atom. And this is also a hydrogen atom. And then we put them together. We get a hydrogen molecule, which is now H2. And we say now that each of those hydrogens has 2 electrons in its valence shell, because those electrons can count for both atoms because they're being shared. The other way we draw this, anybody know? Besides using the dots, what's another way we can express those shared electrons? Well, they're the shared valence electrons. How can we draw them besides the dots? Have you seen before? With a line, right. So another way that we can draw a molecule is like this. And when we draw that line in between atoms, we are specifically talking about 2 shared electrons, exactly 2. Okay. The line doesn't just mean these things are close to each other or these things are kind of connected. It means they are sharing 2 electrons. So when we write something like sodium chloride, we don't draw a line, because sodium chloride is an ionic compound, not a covalent compound. It doesn't have shared electrons, so no line. Right, larger molecules do this too. Let's look at fluorine. F. How many valence electrons does fluorine have? 7. Why is it 7 and not 9? It's in group 7. So those other 2 are in the core, not in the valence. Which means they're not available to do chemistry. We don't care about them anymore. So there's fluorine with its 7 valence electrons. How many electrons does fluorine want to be stable?
1.
Yeah, but how many total? 8, right? So 1 more. So that means fluorine has kind of a space here where it would like 1 more electron to go. It can get that and become an ion, of course. We've already talked about that. Or it can share Do it on this side again so it looks nice. It can share with another fluorine atom and become a fluorine molecule. And another way we might write this is this.
So
Those-
why did you add another atom to the fluorine?
To make it stable. So now each fluorine has an octet. It has 8 electrons for this one and 8 electrons for this one.
Where'd you get 8 from?
8. You mean why 8? 8 means a full shell. So the full outer shell means it has 8 total electrons. Except for hydrogen and helium, it'll always be 8. So, all right, these two shared electrons in this line, this is known as a covalent bond. Covalent, like valence together. They're sharing each other's valence. So it's a covalent bond. And this unit is known as a molecule. So a molecule is multiple atoms covalently bound together or sharing electrons together. And in fact, this is what happens in nature. So hydrogen gas in the air is not just H atoms, it's H2 molecules floating around. Fluorine, like a sample of fluorine gas, is not just F atoms, it's F2 molecules. And in fact, all of the halogens, fluorine, chlorine, bromine, and iodine, all exist as doubles. We call them dimers. But a sample of chlorine gas is Cl2. A sample of bromine liquid is Br2. And a sample of iodine, which is a solid, is I2. They're all in the same place. They all have 7 valence electrons. So they want to connect with another one to make that complete valence. What about oxygen? Let's look at oxygen. How many valence electrons for oxygen? Yeah. So what's it going to do? You know? Yeah, it wants 2 more. And actually, so what it does is it connects with another oxygen. But instead of just sharing 1 pair, it shares 2 pairs. Because if it just shared 1 pair, each oxygen still wouldn't have enough, right? So instead, we share 2. And now each one can have 8. And that's what we call a double bond. So we draw it like this with 2 lines instead of 1. The 2 lines means 2 shared electrons, or 2 pairs of shared electrons instead of just 1. Now when we combine these things together, you'll notice there are still some kind of leftover electrons that we show over here. These are known as non-bonding electrons, or another name for them sometimes you'll hear is lone pairs. These are electrons that aren't shared, but are more on one atom or the other, at least in this idea. These extra dots that are still there, those are part of the structure, and those are known as non-bonding electrons or lone pairs. They don't participate in the bonding in that structure. They're not being shared. They're just on that atom. And we can get bigger, and we can do all kinds of stuff with this. But we're going to take a break from this and go back to naming for a minute, because we need to be able to name this stuff. Molecular compounds get named in a totally different way. And the problem is, it's actually an easier way. And so people get really confused and want to go back and name all the ionic stuff the same way as we name the molecular stuff, and it doesn't work that way. So let's talk about naming molecular compounds, and then let's put it all together with the other names. For molecular compounds, you just say the things, the atoms that are in there, in the same way that you did with the ions, but you don't have to worry about the charges in the parentheses. Because in molecular compounds, we can't really calculate the charges. We don't know how many of each atom is going to be there. So we have to specify it very clearly. And the way that that's done is like this. Oh. Sorry. All right, well, we'll just do it without technology. If we have a molecular compound like SO2, now we're not talking about sulfate ion, we're just talking about SO2. We're going to call this molecule sulfur dioxide. Okay. So we specify with a little prefix how many of each thing there is. The prefixes go mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, and hexa for 6, and we'll stop at 6 for now. So we simply say how many things there are using these prefixes. And we still use the "-ide" suffix for the second thing, even though it's not really an ion. You'll also notice when there's just one at the beginning, we leave mono off. The first one. So how do we name CO? So we're going to leave the mono off, even though there's just one of them, and we'll say carbon. And then we'll go monoxide. So this time we dropped an extra O off because of otherwise it would be monoxide or something. We dropped that extra O off for monoxide. But it's that same prefix because there's one of them.
Have a number?
We still have to name it as 1 because otherwise we don't know. Now remember, think about how this is different from the ionic ones. The ionic ones, we just put the names no matter how many there are because we can always figure out how many there are by the charges. Molecules, we can't do that, right? Whether it's carbon, we couldn't just say carbon oxide because that could be CO or CO2. Those are both carbon oxides. So we have to say carbon monoxide or carbon dioxide to specify which one we're talking about. All right. Right. So these are a little bit more straightforward, especially going from the name to the formula. For instance, this one. Dinitrogen monoxide. So how would you...
N2O.
N2O. This one also has a common name, which is nitrous oxide. This is our laughing gas. Anybody ever get to have some of that?
I didn't even listen to it before.
Like at the dentist or just from whipped cream containers? Oh, yeah.
It was pretty alright.
Yeah, it's not bad.
I didn't mind all the blood and stuff.
Right. Kind of relaxes you. You don't care so much about what's happening. Yeah. So technically, systematically, we would call that dinitrogen monoxide or just dinitrogen oxide because there aren't any other ones. All right, how about this one? How would you name this one? What's the first one called? Silicon.
Silicon tetra.
Yeah, that's it. You got it.
Wait, SI is
Silicon. Tetrabromide. So while we're talking about this, let's do a little sidebar here and talk about the difference between silicon and silicone.
yeah.
Silicon is the element, Si, right? Silicone is a polymer, which means it's a huge molecule that is made up of oh, now I'm going to get confused here. Silicon and oxygen bonds and some carbon as well. I think that's right. I'm actually not sure, so this might not be right. I think that's right. But it basically has silicon and oxygen with other stuff connected, and it keeps going on in both directions for thousands and thousands of molecules. Yeah, with oxygen and carbons in it. And silicone is a really important material. Anything that it kind of has like a rubbery feel to it, like phone cases or materials in cars or like grips on pens that you sometimes get. Anytime that kind of has anything that has that squishy, rubbery feel, that's what that's made from, silicone. So I mean, it's everywhere. It's an additive in anything from like some creams and lotions to a lot of materials that want a little bit of that. It's a glass additive. It's a huge part of the materials we use. What? Implants, right? Yeah. Yeah. And there's lots of different kinds of silicones depending on what's connected to it. There's squishier ones and harder ones and all kinds of different. So it's a whole area of chemistry on its own. But what we're mostly going to talk about is the element silicon. And this element by itself, this is what's used in things like computer chips. Very pure silicon. We use its because it's a semi-metal or a wow, I can't think of that word right now. Metalloid. It means it's a semiconductor, and so it's very important in computing applications. So make sure you don't throw that little E on the end of it, because it's not right. All right, let's keep thinking about it. Careful. B2O3. Diboron trioxide, right? So see what I mean about how this one's a little bit more straightforward? You just always say whatever numbers there are. The danger with this is now that we've learned this, everybody wants to go back to the ionic ones and name them differently. So everybody goes back to TiO2 and now names it titanium dioxide or chromium trioxide, which is actually okay in certain cases. But generally, you know, strontium dinitrate or tripotassium phosphide, those names aren't right for ionic compounds. We don't use those. Those are only for the molecular compounds. And the reason for that is that it allows us to separate one from the other based on how we name it. And depending on how we name it, we know which kind of compound we're talking about. So the book has this nice flow chart, which we're going to kind of reconstruct here, about how to name anything. All right, so you're going to start with of these types of things that we've talked about anyway. So the first question is, is it an ionic compound or is it covalent molecular compound? How do we figure that out? How can we figure out if we're going to use the ionic rules or the covalent rules if we just see some random compound that I put on the quiz and you have to come up with a name for it?
Well, isn't something a metal? A metal is not.
Yeah.
Right, exactly. So if it's ionic, it will be a metal and nonmetals. But especially it'll have the metal. If it's covalent,
Non-metal
it'll be nonmetal.
and non-metal.
Yeah.
Right?
Yeah, everything will be nonmetals.
Oh.
For the ones, and these rules aren't totally perfect. There's lots of compounds that you name differently that metals can be covalent, but we won't get into that in this class. So if you got nonmetals and there's no metals in your formula, which you can figure out by looking at the periodic table and seeing where stuff is, right?
Mm-hmm.
Then it's pretty easy. You go and you use your prefixes that everyone loves, your mono, di, tri, stuff that we've just been talking about. Once you know it's ionic, or once you know it's covalent and there's no metals around, you can go ahead and name it di, tri, tetra, all that stuff. If there's a metal involved, then you have to make another choice. Your next choice is to look at that charge in the metal. Look at that metal. Does that metal have a fixed charge where it always takes the same charge? Or can it take some different charges? Like, if it's potassium, something in that first column, K, we know that's got to be +1 because the metals in that column are always +1. They don't take any other charge. They've got to be +1. So that's an example of a fixed charge. But if we have iron, Fe, which is 26, that's in the middle in that transition metal space, and we know that that has some variable charges. It can take some different charges. So that one fits the other side. How do we name it then if we have a fixed charge? If it's fixed, it's without the parentheses. If we know the charge, it's without the parentheses. So that's going to be something like potassium iodide, right? K, which is Ki. We know K has to be +1 paired with the I, so it's potassium iodide. If it's a variable metal charge, then we have to specify with parentheses, and that could be generally the transition metals. So we'll stick with our iodides here, and we could have CuI2. Actually, copper iodide is usually copper 1, so we'll go copper 1 iodide. And let's give an example here. We could have phosphorus triiodide, which would be Pi3. All nonmetals. So the other bit of a wrinkle here then is the polyatomic ions, because we haven't really talked about that. they're only going to exist on the left with the metals. And if you have a polyatomic ion, none of these rules change. You just use that as your anion name instead of whatever the other one is. So now we got all the rules. Let's practice. How do you want to name Fe2O3? So let's work down the flow chart. Is it going to go ionic or covalent? Ionic, how do you know? Yeah, because you've got a metal, right? Iron, transition metal. Which side of the ionics is it going to go on? Fixed or variable charge? Variable, how do you know? Transition metal. So that means that we're going to have some name, parentheses with a number in it, and then another name. What are those blanks going to have in them? Well, the charge will be in the parentheses. What are we going to put on the lines here? Iron and oxide. So we're not going to call this di-iron trioxide, right? Because it's an ionic compound. So what are we going to put in that parentheses? What's the charge on iron? How do you know? You got to calculate it out. So we've got, hang on a second, I'm going to. So we've got 3 oxygen atoms and 2 iron. Each oxygen we know is going to be -2. So what does each iron have to be? +3 to balance it out. And then what do we put in the parentheses? 3. Each iron is +3, so we put a 3 there. So it's iron 3 oxide.
Will you give us problems like with that answer? We have to figure out the formula.
Yep, let's do that. Iron 2 sulfate. So you can look it up for now, but for next week you're going to know that sulfate is what? SO4 -2. So then what does the iron have to be, or the iron, what is the charge on the iron going to be based on the name? What's the charge? +2, because of the parentheses tells us it's got to be iron 2. Iron 2 means iron +2. So then how do we put these together? Just like that. You got 2 plus, 2 minus. We don't need to adjust any numbers. They balance out just fine. So the formula should be SO4. So we'll stick with this one, aluminum sulfate. Now aluminum is a little bit tricky, so we'll just have to know that one. It's not in the first 2 columns, but it always has a fixed charge. Anybody know what it is? Take a look at where it is on the periodic table. It's Al. What do you think might be its charge? 3. Yeah. So aluminum is always 3 plus. So now see if you can balance the rest of that formula and get the full formula for aluminum sulfate. So once again, what's sulfate? All right, so how are you going to get these things to balance out? Yeah. Is that what you're saying? Go ahead. Okay, what were you going to say? Yeah. So the 3 and the 2 are never going to balance out if you only change one, so we're going to have to change both of them. We need 2 aluminums and 3 sulfates. How do we write that all together then? Yeah, Al2 SO4 3. Good. Okay, let's try this one. I'll give you the formula, you give me the name. Yeah, say it again. Uh-huh. Close. You're only one letter off.
Fluoride.
There you go. How did you figure that out? Yeah, these are both nonmetals, so it goes the covalent route. And we use the prefixes. We leave the mono off the first one and we just say selenium. And then there's 6 fluorines, so it's hexa.
The aluminum sulfate was a ionic.
Right. Because of the metal there, the aluminum. Okay. This is an important part of fertilizer, ammonium sulfate. You didn't come up with a formula for that one. And then if you got that one, come up with a name for this one.
For the hexafluoride, the F, the cut is from fluorine, right?
Right.
So why would you change the last 3 letters? Because I know that was like oxygen, if it oxidized something.
Actually, anything will change the last. Any of these names, we change the last 3 letters.
Oh.
So oxygen becomes oxide, fluorine becomes fluoride, sulfur becomes sulfide,
Okay,
bromine
so it's
becomes
all
bromide.
At the end of it?
Yeah. Unless we're talking about a.
Bromide?
Yep.
Really? Oh, okay.
That's one of the polyatomic ions. So, what is, anybody remember ammonium?
NH4.
Yep. NH4 plus 1. And sulfate? Yep. So see if we can put those together.
This is the polyatomic.
Is it back?
What do you mean?
The ammonia.
Let's think about it. So this is this is really the only example of where you don't have a metal, but it's still an ionic compound. You have two ions, two charged particles, ions, that are made of nonmetals. When you see that NH4, as polyatomic ions, you should think about that is an ion. Think of it, make sure you remember that it is an ion. That's why it's named this way. So to figure out how many we have in the formula, we need to balance the charge, just like any other ionic compound, which means how many of these do we need relative to this? One more. We need two of these and one of these, and the way we would write that is like that. Yeah, because in this case there's just one of them, and when there's just one, we don't use the parentheses.
Why did you add another ammonium?
Because each one.
To balance it, but it's already the hydrogen, right? The sodium, hydrogen, ammonium.
The nitrogen?
The nitrogen, sorry.
Yeah.
It's already 4. And SO has 4.
Well, we're not, remember, we can't think of these things as individual atoms. They are a whole ion. NH4 plus, you can think of it as just like X plus. Doesn't matter what's in there.
2 minus?
It's all together. And then the sulfate is 2 minus altogether.
Oh, okay.
So you need 2 of those whole ammoniums to balance out the sulfate. Does anybody get a name for the next one yet? Before anybody says anything, everybody write down a name for this one. Do the best you can, and see if you can write down the name. And then we'll see how it goes.
The CACM, that one you were working on?
Yeah, the CaCO3.
What would be the small carbon
Carbonate.
You hear that? So this is one of those polyatomic ions from the table up here. Carbonate. Mm-hmm.
Do you want us to balance it out now?
I just want the name, the correct name, whatever that is. All right, who feels good about this one? I said, who feels good about it? You got it? Go ahead.
calcium?
Yep, good. So this is calcium carbonate. Why don't you put any number in parentheses there? Because it's, sure. Yeah, it's in the second group. We know it's got to be +2. It's not a variable charge. So that's it. Okay, here comes another one. This is rocket fuel. 204. There you go, nice. Dinitrogen tetroxide. If you said tetraoxide, that's all right. You're getting this. Let's try for more. Okay. CRPO4. Just want the name, but the full and correct name. That's the tricky part. This is capital P, capital O. So what does that make it?
Phosphate.
Phosphate, right? This is a polyatomic ion.
Why isn't it phosphide?
Phosphide would be just P. Right, because of the oxygens there. Well, if it's P as an ion, a negative ion, it's phosphide.
Oh my God, these are so confusing.
So if it was like CRP something, that would be phosphide. But because of the oxygen there, that makes it phosphate, one of the polyatomic ions. Think about it this way. You don't see these having separate names. Like we don't see any names that have chromium, phosphorus, and oxide in it. So if you are getting to that, if you're getting confused by that and you're thinking, it's weird that I have to put like 3 different names here, chances are you're missing that one of them is an ion all together itself. So in this case, phosphate is on our list.
Yeah.
PO4, it's a 3- ion on its own. So we call that phosphate. It's on the list. So for now, look at the list, but by Wednesday, make sure you have that list in your head.
Is this what we're doing on Wednesday?
Phosphate, the polyatomic ion.
Can you go back to that slide?
Mhm.
Okay, yeah, it's exactly. But like,
It's still chromium.
it's hydroxide.
What?
OH.
OH is hydroxide. So this one so far we've got chromium and phosphate. So are we done? Is that it? Yeah? Okay. Wrong. Sorry. What's wrong here? What do we need? What's wrong with this name?
It's just so many of them.
Let's go back to our flow chart right here. It breaks it all down. So we figured out it's ionic, right?
Is PO4 and
Yeah. Right. So we figured out that it's an ionic compound. So is it a fixed charge or a variable charge for chromium? It's variable because that's right in the middle there, number 24. So what does that mean we're missing? Right, we need our parentheses. Go ahead.
Phosphate is minus 3, so you have to
Plus there, oh.
So phosphate is -3. That's what we know from our table, from our list, which means we need a chromium +3 to balance it out. So that means this is chromium 3 phosphate.
But if you write that in it,
instructions on the inputs, out is right.
yeah,
Nope.
because the setting is wrong.
What? I know. But that's what's tough. That's why we have the flow chart. Because if you don't know which one we're talking about at the time, you have to make the decision which parts to put in and which parts not to. So you have to think about it as first ionic or covalent, then if it's ionic, fixed or variable, and that tells you which way you have to go. You only have to make 2 choices. That's not too bad, right? Yeah, we'll do some. Okay, let's try another one. You want to do, I give you the formula and you name it, or I give you the name and you give the formula?
I like these.
Surprise? Okay.
I like the whole mono, di, tri. I like that.
All right, but if I just do that now, then everybody's going to be thinking of that way.
No,
And
I'm
then,
just saying, can you put that on the test, like majority, please?
no,
Come on, whatever.
it will be on there. I'm not going to say what's going to be more.
More of those on there than us having to pick whether it's.
Well, look, take a look at the quiz from last year on Blackboard and see what you think.
The one you put on there for exam 1 wasn't much.
Yeah.
That's true, but that was probably good, right?
Only a few questions from you. It's so much that we do.
Well, yeah, because I'm not going to ask the same questions again, right? Doesn't take much thinking if you just sort of remember the old stuff and then. All right, what was I going to write here? Magnesium something. Mg3N2, let's give a name for this one. Well, you have to make that decision. Go back to the flow chart. Let's think about it.
Right? So metal plus non-metal is ionic. So now we have to pick or choose if it's fixed.
Wait a minute. Do that.
The name, yeah.
You have to balance this out, right? Obviously.
Well, you have to find the name, whatever that entails.
I think it's magnesium, parentheses, Roman numeral something.
Yeah, so once you think you got a name, I know some of you have already done this, but talk to the people next to you. See if your names match up. If you haven't, think about why they might be different.
Well, nitride, magnesium nitride. Is this going to be multiple choice?
No. No, you're going to come up with the names.
Like on the test?
Mm-hmm. No.
Is it magnesium
Maybe. I don't know.
nitride?
Yeah.
It is? Are
Yeah.
you lying?
No.
You swear?
Yep.
And MG, you want us to balance it?
Oh my gosh. Shh. Don't give me your.
This is the name.
Two.
That's it.
Do we have to balance? That's not. It's not it.
Why don't you need the parentheses here? What? What's the point of what numbers? Because we have magnesium is +2 and nitrogen is -3. So in order for magnesium and nitride,
Balanced out.
yeah, it's there for you in the formula.
Oh.
That tells you how many of each you have to have. The only time you have to mess with that is if you need to put something in parentheses. And why don't you here?
Because it's on the middle of the periodic table?
Right, it's a fixed charge. We know magnesium must be +2.
I get it.
Mhm.
When you go MG and 2.
It's already.
Mg3 and 2.
Oh, that's always there.
Yeah. You just didn't copy it down right then, yeah.
What if you give us, like, the name to put the formula?
Yeah.
And someone like MG, then N2.
That's the wrong formula.
Where's the three? Where's the?
Balance it out.
Yeah,
So
balance it
let's
out.
see how it would go the other way. So let's pretend that I said magnesium nitride instead. So what do? We start with the two ions and we figure out their charges. Magnesium's charge is what? And what about nitride? -3. So you say, okay, how many of each of these do I need to balance out the charge? Well, they're not going to balance out if I only change one because it's 2 and 3. So I'm going to have to change both of them. I need 2 of these to get 6, and then I need 3 of these. So then I would write down Mg3 and 2. And that's where that formula comes from. It wasn't a trick. It's just writing the name of these things. That's it.
Look, we wrote nitride. Give us another one.
So here are some of the things that I will probably see, not from you, of course, but from other people who aren't as well practiced in naming these things. So when I say Mg3N2, somebody's going to write trimagnesium dinitride. So what's the problem with that? Yeah, this is an ionic compound, and that's the name of a covalent compound of all nonmetals. This one here, chromium phosphate, someone's going to name that chromium phosphorus oxide or chromium phosphide oxide. What's the problem with that?
It's not already.
Yeah, it's all together as one ion. It's phosphate. So you got to sit up front so you can get out there, get your answers out first. You got to sit up front so you can get your answers out first. You guys get to answer all the questions.
Yeah.
All right, a couple more, we'll call it a night. All right, here's a formula, and then a name. Yeah, let's see if we can get a name for the formula on the left and a formula for the name on the right. I have to look that one up. If you don't have a periodic table with you with the names, somebody else say what tin is. Anybody find it?
Is that a C and an L or an I?
CL.
CL.
I always make my eyes with hats and feet or whatever you want to call that.
You want us to write the formula for the second one?
Yeah, formula for the second one.
Non-metal and non-metal is covalent, right? Yeah.
See what you can do with this. I'm not going to give any hints, and then we'll go through it in a couple minutes. See if you can get a name for the one on the left and a formula for the one on the right. This definitely takes practice. This is the first time we've talked about it. It's night, you know. It's going to take some time of you sitting home with some problems to really work this thing out. But I think we got a good start. Yeah. Because it wouldn't make sense the other way around. You just rewrite what I wrote.
That Roman numeral is in charges too. But that's not the charge.
But it is. What's the formula for tin? It is, but it's kind of under the staircase, so those are really more variable. Yeah.
You gotta keep the charges for the first for 10, how to rewrite it is the formula. Do not keep the charge number. You still put it in there.
You don't put the charge number in when you write it as a formula. For what?
The 10.
Right. Right.
Everything under the
So we don't have to put the
Except for aluminum, yeah.
Okay.
We're not doing the charge.
You're rewriting it as a formula. So you wouldn't
Is it SN2CL?
All right, everybody's got some names and some formulas? Okay, what do you got for the first one?
Sulfate chloride?
There we go.
There we go.
Good job. Sulfur.
come on. That's kidding. Yeah, seriously.
How did we know it was one of those?
It was non-metal and non-metal. It's
Yeah.
covalent bond.
There's no metals here, so we've got to use that other way to name it.
Wait. Okay, hold on.
If it's a metal and a non-metal,
Then we go the other way. All right, what about the formula for this one? Yeah, go ahead.
It's Sn plus, would be plus 1.
How'd you get +1 for the SN? Okay.
Was it right?
No, but that's you're close. We know the charge here. Anybody know how we know the charge? We don't have to guess. It's 2. How do you know it's 2? Because it says 2 in the parentheses. So we know this is going to be tin plus 2. And we know that carbonate is 3, 2 minus. Yeah. So we stick them together. So we got SnCO3. No, because we only have one of them. If we had more, we would put it in parentheses. Yeah. So, I mean, if we had a 1 plus, that's good that you know to go with 2 of them, but in this case it was 2 plus. So. All right, so practice this up, and we'll check it out next week. So Monday lab, make sure to get the pre-lab. I'll try to get all the grading caught up so you can see kind of what's going on overall in the class. And enjoy the rest of your week and weekend.
We have to do the pre-lab or whatever. What lab do we have?
We didn't. We skipped one
What is it? What that was-
that we missed on Labor Day. No, that's the exam was on the schedule, so it should be whatever's next on the schedule. I don't remember.
that's fine.